Always forget to turn that thing on. All right. Did you have a question, Andrew? Somebody?
No.
So the first example of these three pulleys, there's 1-to-1 here. Here we, if you look at it, you can see if you have T, and I'll look down, you can now see the sort of, I won't call these free body diagrams. I will call this drawing on your sketch. I'll show you what I mean by what I think a free body diagram ought to look like in just a minute. But here you can see that we're going to have, actually this arrow is drawn the wrong way. It's my error. Arrow should be going up. We'll have 2T pulling up and on the load, so the load will equal 2T, and we have an advantage of 2-to-1. And over here, we have a system of 2 pulleys, and if we go through the same thing, we actually end up with the same ratio of 2T. During this lab, I'm going to have you look at the attach points for the pulleys. You may not have been doing that on the problems, but it's an important engineering aspect, because a lot of times people attach pulleys to the top and they don't realize that that attach point where the pulley is sometimes going to be greater than the load that they're lifting. So they think, oh, I've got a 500-pound weight. I only need to have a beam at the top that can hold 500 pounds. Well, in this case, the answer would be no. You would need to have a beam that held at least 1,000 pounds. Because if this load was 500, you'll look here, you'll see that F is equal to twice the tension in the rope. So actually, I shouldn't say that's actually incorrect. It's not twice the load. It's going to be 2T, and T is going to be half of the load. So it'll be 500 pounds. So it'll still be 250 pounds. My apologies there. Kind of overstated that. But sometimes this can act as a multiplier, such as over here in this first case where the fixed pulley is. We actually have the load of 100 pounds or 500 pounds. It is going to double the force there at the top. And that's why it's important to do these calculations. So real quick, I'm going to switch to a different camera. I'm going to stop sharing for a second. All right. So I wanted to show you what is meant by a free body diagram in this case, and what it ought to look like. So we had a pulley from the roof. Everybody see that? Or should I be doing bigger?
Oh, it looks good.
Yeah, looks good.
Okay. So we've got this rope that comes down, and if you want, you can draw it like this. It's pretty easy to do it diagrammatically like this. And we would have T, and some F. To me, what a good free body diagram would look like is going to look like this. Oh, I'm going to get rid of this one. That one. You just draw your pulley. And then we could do our equations. Some of the forces in the y is equal to 0 is equal to T minus T plus F. That is the essence of that really quickly. If we solve for F, we have 2T. So that's how you would draw a free body diagram for that. And we can do that for each and every pulley. Let me go back to.
So Robert, that's not a particle anymore. That's a whole body diagram, right?
It is indeed, and that's a good point. Later on, we're going to do. I have a lab on just how to draw free body diagrams, and we'll go through this. But I'm showing you how to do pulleys right now. And this is one of the key reasons why I want all the forces to be vertical. That's why we're making that assumption. Once we get into the forces going in another direction, we'll start to have torque. We'll start to have other problems. We'll have to start worrying about friction. I've got a whole lab planned on how to do free bodies that are not of particles. But by doing it like this, it is very similar to a particle free body diagram. So this is kind of an intermediate step. So let's go back to here. So let's just look at this last one here real quick, and I'm going to draw the free body diagram for each of those. I'm going to get rid of the I'm not going to draw the sketch. I'm just going to draw the free body diagram. You guys have the sketch in front of you. If I pull that sketch up, so I don't need to track. So the free body diagram of the movable pulley. Let's just do that real quick. That would have T and T and W for the load, whichever you like. So that would be the movable pulley, and then the fixed pulley. This is, like I said, this is all pretty straightforward stuff, but if you follow this path, it'll make all of this so much easier. And I don't expect your drawings to be much more complicated than what I've just done here. So by looking at this, we can now determine the ratio between W and F. Like I was saying earlier, we know that W is equal to 2T. We know that F is equal to 2T. And so by substituting for T, you can say F is equal to W over 2. Is that right? So I make T equal to W over 2 times 2. So in this case, F equals W. So I'm going to move on to the next set of examples. Is there any questions at this point on that? That all seem pretty straightforward.
Just for clarification, what you were drawing there, that was all one system. You just basically broke it in half, right?
Yeah, I was breaking it into a free body diagram for each pulley.
Right.
And the pulley that I had in mind was this one over here, the fixed and the moving.
Right.
So it was a system of 2 pulleys, and I broke it into 2. So one other important point to note when you're designing systems, and I'm always surprised, but I think I now know enough to say something. You won't get any mechanical advantage from a pulley unless at least one of them is a movable pulley. Otherwise, all you're doing is rerouting the rope through a snake-like pattern. It seems silly, but every year when I see people building little pulley systems on the board, there's always invariably at least one group that builds a bunch of pulleys and none of them move. and they're surprised at how difficult it is to operate, and that the weight doesn't really cause any mechanical advantage. So you at least have to have a movable pulley. So keep that in mind. All right. So here's another one, another example. This is very similar to what we looked at. You can see here they've actually got the numbers right on there. There's the 100 newtons coming out is equal to load. This is a 1-to-1 mechanical advantage. Here we get a 2-to-1, and you'll see that we have an attach point that has a force of 50 newtons at the top, and it's half of the load. Whereas here you'll see that the 100 Newton load creates a greater load at the attach point. So, like I said, the attach point actually is pretty critical. Like I said, a lot of times people forget that part. They forget that the pulley can actually increase the load on the beam. So, if you think about it, it kind of makes sense because we have a load, and then we're also pulling down with 50 Newton meters, so it would be the additional of two. So, in theory, you could do a free body diagram of the whole thing, but we're not doing that. I think David pointed out that we're no longer drawing free body particles, and so I'm going to kind of keep it simple, and let's just draw of just the pulleys.
That's
So
way cool.
What's that?
I have definitely run into that, and that's way cool. That explains a lot.
Yeah. So it's kind of why I'm going through this, because when you go to design stuff, you'll need to be able to do this, because otherwise you'll just be, going around circles. So let's draw a free body diagram for this top pulley. I'm going to stop sharing and switch my camera again. And let me pull up the diagram so I know what I'm looking at. So let me draw that top pulley. Actually, I'll draw both pulleys. I think it'll help a lot if I draw both pulleys and solve it. So let me draw, we'll draw the lower pulley on the left here, and I'll draw the other pulley up here. And I'm drawing them separately again. And so for here, we've got the load. Let's just call it W. And then we've got tension and tension. Now notice again, the tensions are equal all the way through. So I could just label it T. If I have more than one rope, I'll show you, we just do T1, T2, etc. Let's do the other one real quick. And up here we have the rope that we're actually pulling down, T. We have another T. And then we have one more coming from the center, T. And then we've got this attach point, F. So in each of these situations, if I do some of the forces in the Y direction, here I have T plus T minus W equals 0. And over here, I'm going to have, again, the sum of the forces in the Y always equals 0 is going to be minus T minus T minus T plus F. So here I'm going to have F equals 3T, and here I've got W equals 2T. And so I can solve for the ratio of W to F to find out what the force is on there. This is my mechanical advantage right here, down here. Can everybody see that? And if I wanted to solve for that, I would solve for T here and substitute back in. So I'm going to have F equals 3 times W over 2. And so F equals 1.5 W. If you went back to that original diagram, you'd see that that was indeed the case.
So just to be clear for everyone, so you solved for T on your W equals 2T equation, and then you back subbed the T into the other equation. Just to be clear. Correct.
Yeah. All right, there's a lot to swallow, and this is kind of a long stretch for me to be talking. I say that long stretch, it's not that it bothers me to talk for a long time. In fact, I can talk forever. I've been known to do that. My concern is that people start to fall asleep. I start to sort of feel like a lullaby rather than an instructor. So we're going to move on to the next one. All right. Oh, back to this one real quick. You can see here was a movable pulley. There's always a movable pulley in there. Even though we have a fix, there's at least one movable pulley, so we're getting an advantage here. No movable pulley, no advantage.
Rob?
Yeah.
Can you explain to them the advantage? Because I know like our equation shows that the force is has a ratio to the weight, but could be confusing, I think, a little bit. Just explain like how much of an advantage you get based off the equation, maybe.
Yeah. So yeah, I think you can still see down here. We say the weight is equal to 2 times the tension, or more importantly, if you were pulling on that thing, with you be pulling the tension, it would be half the weight. So you're going to get an advantage of 2 to 1.
Right.
So if you could lift 100, if you can pull with 100 pounds, you can lift a 200-pound item.
Exactly. Yeah.
So, and these, let me box this. So what I'm asking you to do in the lab is I'm asking you to come up with this mechanical ratio here, W versus some version of T that you'll be pulling out wherever you're pulling that T, and the weight that you're trying to lift, and any of the attach points. And we may have multiple attach points like we will in the next one. When you get to your answer like this, please box them. And I know that you know what you're looking for, and I know how to look at the problem easily. I've kind of said this to a couple of people already. Part of engineering is learning how to communicate what you know to others. It isn't just knowing the material. If you can't communicate your knowledge to anybody, you're not helping. So part of this is about being as neat as you can and as clear as you can. I struggle with neatness big time, so I have a hard time giving people a hard time about being neat, but sometimes, yeah, being neat is very helpful. All right, let's go back to here.
So just to clarify then, can I?
Yeah, go ahead.
So the force on the ceiling is 1.5 times the weight that we're pulling in that last example.
Yes, correct.
Okay.
So that's why I was saying it's important to know the attach points, because if your beam was designed to carry only the load of the weight, it would be bad. And in fact, if we look at that example, we go back to the screen share. Yeah, in that case, it would be 1.5 times.
And just another summary. So the mechanical advantage allows you to pull more weight with less force, but it adds more total force on the beam attaching the fixed pulley. So the beam needs to be stronger so it could hold more force, but you could apply less force to lift up more of a load.
Yeah, yeah. Doesn't always quite work out that way. Like I said, the first example, it's a 1-to-1.
Right.
Let's look at
Well, and also the tension you have coming off here is at diagonal.
Yes.
If that was coming horizontally, you wouldn't be applying a vertical downward load to the beam.
Actually, it would still apply. There would be some horizontal load, yes, but the load would still be greater than the load of the weight.
If the takeoff was horizontal.
Yes, it's still, because now the whole, what's going to happen, and we're not getting into this. This is just an aside, so please don't focus on this, because you're just going to confuse yourself. Again, for the purpose of this lab, we're going to assume that everything is vertical. They draw it this way just so they know where you're pulling. But what would happen is now you would have a Y force, and this whole thing would want to tilt over, because this isn't a rigid connection, most likely, and so it's going to have an angle. And we can, later on when we start to draw other free body diagrams, we can look at a pulley that's being pulled from the side. But we're not going to do that today. That's just going to mess everybody up. So for today, just assume that everything is vertical. So here's another system, and this is a 2-rope system. There's one rope attached to P1 that goes down through this lower pulley and attaches to the middle pulley in the center. And then we have another rope that starts at P2, goes through the middle pulley, goes to the upper pulley, and then is pulled down by whoever there is pulling on it. And again, it's shown at an angle, but for the purpose of calculations, let's make sure that we consider it vertical. So I'm going to go through and draw each of these and show you how to figure out what the mechanical ratio is, or the mechanical advantage. All right. So I typically find it easier to start with, oh, you guys can't see it, sorry. Can you see this diagram? Yeah. All right.
Yes.
I typically find it easiest to start where the weight is. You can start solving the problem from either side typically, but I usually find it easier with multi-rope systems to start with the weight. And we'll work that way, and you'll see why, I hope. So I'm going to go draw each of those individually on my board. I'm just going to do the free body diagrams. Here's my first pulley. And I'm going to have W and T and T. And I'm going to label these T1. All right?
You have it labeled T2 in the example.
Okay, yeah, let me be consistent. Thank you, Andrew. I probably should have labeled it T1 in the diagram because it's attached to point 1, but
Right.
let's do that. T2, T2. And right away, if we just look at this diagram, we can see that the force at P1 is equal to T2. I don't think we even need to draw a free body diagram for that, but if you'd like, you can. Here's the next one. So here's the difference here. We see we've got T2 here, and then we have 2 T1. And then lastly, this last one, I'm going to have T1, T1, and I'm going to call this F3 because it's attached at point 3. So down here, and I'm going to skip the notation for brevity. I'm not going to show some of the forces in the Y, but that's what we're doing. We end up with W equals 2T2. This isn't what we're finally looking for. We're eventually looking for W in terms of a ratio to T1, which is where we're pulling from. So this isn't our final answer. We're not going to box this, but we're going to keep this as an information for us. Here, if we do again, we did the sum of the forces in the y equals to 0, we would have T1 plus T1 minus T2, and we would end up with T2 equals 2 T1. And then lastly, up here we would have F is equal to 2 T1. All right. So if we wanted to get the ratio of T1 to W, these two items here, we're going to need to use this intermediate equation. So I'm going to basically solve for T2, which it already is, and substitute it into this equation here. And that will give me W is equal to 4 T1. And that's our final mechanical advantage ratio right there. So we could pull with 1/4 the weight. So if we were to solve for T, it would divide by W. So that's our mechanical advantage. This is our solution for, and this should have F3. This is our solution for this attach point. And then we have F2, which should just be equal to T1. And then we have F1 will be equal to T2. So now in essence, we've solved for every pulley there, and we have our solutions, we have our mechanical advantage ratio, and we have the forces on each of our attach points. And I hope everybody gets that.
F2 doesn't seem trivial because there's multiple things kind of stacked below it. Maybe that's just sort of like a misconception or an illusion because we're computing one, but it doesn't look trivial to me.
Let's go back. So if you look at this diagram, we can see that the T1 is the constant tension through that entire rope. And the only thing attaching to P2 is that first rope labeled T1. And so can only be T1. It's the only force on there. So that rule about how the rope is constant tension throughout the entire thing holds true and is true at P2.
Okay. I mean,
I know.
A layman, it might look funny because T2 is also pulling down at that kind of vertical spot. But
absolutely.
Okay.
And we're trying to teach you guys to be other than laymen.
That's fair.
So when we get into trusses, there is a series of things like this that throw people in trusses to no end. Their intuition tells them that there ought to be a greater load there when there isn't. I would say trust the math and the process, and you'll come up with the right solution. Hopefully what we're doing in this class is building a new sense of intuition rather than your old sense of intuition. So I'm going to go back to my other screen here. Stop sharing. And I'm going to go over to, I built this very system on a pulley setup. And hopefully you can see it. So this is the same system right here. This is that same setup that we just did. This is where I would pull. And we said that we had a 4-to-1 mechanical advantage, that we could lift something that was 4 times as much as I pulled on this line here. The other thing that I mentioned earlier on is that I talked about not only is there mechanical advantage, but if I pull on this item here, you'll watch what happens to this weight. When I pull this down 4 peg drops, this item only moves up 1 peg drop. So I have to pull this distance 4 times as far to lift the distance that I want it to go. And that is one way you can check your systems in reality, in the real world, is if you think you have a 4-to-1 mechanical advantage, you should have to pull the rope 4 times as far as you normally would. So that's something that a lot of students miss in the process, but this is a design check you could have in the real world, is to make sure that you have to pull the ratio that you've just created as a mechanical advantage, means that you have to move it that much further in distance. So I wanted to look at one of these pulleys like these over here on the right.
Robert, real quick on that last
Yes.
one. So the force 1 is equal to force 3. And is that an assumption we could make because those are the places where they're attached? The rope is directly attached to the beam at P1, and then the pulley is directly attached at P3. So kind of like, is it always safe to assume that those would be the same in a sense? Or why the significance of them being the same? You know what I'm saying?
I haven't done, yeah, quickly we have force 3 is 2 times T1, and
F1 is T2, which is equal to 2T1.
right. So T2, yeah, okay. Yeah, so in theory, F1 and F3 are equal, yes. But F2 is going to be half of that, as I recall.
Right, and I was just gonna see if there was you should know that that's true. Like you should be able to check in your head mentally that should be the case. And,
Yeah.
Okay. Yeah.
Kind of
Okay.
makes sense. I wanted to introduce these kinds of pulleys because this is something that will be at your arsenal. This is a double pulley. You can see they're attached to each other, so they're one. So this whole set of pulleys is, non-moving, and this is the moving. So we really have 2 moving pulleys, but they move together as a unit, and these move together as a unit. And I wanted to talk a little bit about, and I'm going to move over to the board in a minute. Now you can see this, and we could measure this distance now and determine it. But I'm just going to show you how to draw a free body diagram of one of these, particularly here. Because part of what we're doing in a free body diagram is making it free from everything else. And so I would cut this here, and that would make it free. When I cut here, I have to cut here and here. And then we need to draw all the forces as a part of that. So again, a free body diagram is cutting it free from its system and then replacing all the attached points with forces to make sure that it stays in equilibrium, i.e. in static, not moving. So there are other ways to do these kinds of pulleys. This is a 2 pulley. I don't know if you can see this very well. This is a 3 pulley, 1, 2, 3 across, rather than stacked vertically. Like this is stacked vertically. And these are really, they're in essence the same thing. If you were designing something in the real world and you were concerned about the amount of vertical height you had, like say you were trying to lift it over a particular item and your beam was only so far above, you would probably choose a situation more like this where you're going to save some vertical space. But both of these achieve the same thing. This is probably a more common look. And they come in ratios of up to 4. You can have 4. This is one that actually would do something. So, I'm going to draw this top diagram for you over on the board, and then look at the free body diagram.
To be clear there, you were comparing a 2 and a 3. Right.
2,
they'll do the same thing if they have the same number of wheels.
yes. If I don't have a 2, well, this would be the same. That's what I did, was take this. I was just trying to show you that they come in different arrangements.
Mm-hmm.
And so that you know that they come in different arrangements. Because when you guys, the whole point of this lab is you guys are going to design some systems, and you need to know what is available to you to design. Let me come back here. Well, this is as big as my whiteboard gets in my home office. So normally I would just sort of go on to another whiteboard.
I love your vice clamp you've got there for it, though, Robert.
I couldn't figure out how to do it without making it permanently mounted to the wall. This is actually the whiteboard from my office that I stole. I keep one in my office for discussions, particularly with folks who don't understand what I do. This allows me to kind of talk with my hands. All right, so let's look at that top pulley, and let me kind of show you how I would draw it diagram-wise. This will be the diagram. This is not going to be the free body. So we'll have the fall. And typically what I'll do is I'll draw a bar through there, a dot, and a dot, and a dot. And we've got the same thing here. So this is an acceptable drawing for what we're doing. And what I've got, I'm going to draw the line in green, because I've got my, this is going to be where I'm pulling. This comes up and around, comes down, comes around, comes up, around, and goes back. And then I have an attach point, and then I have my load. So if I want to draw the free body diagram of the top pulley, and draw just a top pulley. And so my sum of the forces in the Y here would be F equals, excuse me, F minus T minus T minus T minus T minus T equals 0. And so F will equal 5T. So that would be my force at the attach point. Let's draw the bottom one real quick. And we'll draw it just over here. And And rather than doing it longhand, I'm just going to give you the solution is equal to 4T. So that would be my mechanical advantage on this one. And you can see that the attach point is just a little bit greater.
Can you explain in words the mechanical advantage again?
Are you talking in terms of the solution?
Yeah.
Yeah. So this is the mechanical advantage right here. It's W. Because what I'm looking for is a ratio between here and here. So I'm trying to find out what's the ratio between the T that I'm pulling on and the weight.
Right.
And so the ratio is going to be this. It's going to be this final solution over here. W equals 4T. I'm gonna leave that up there for a second or two.
In this case, would we have a 5/4 mechanical advantage?
No, this is not expressed as a ratio between W and T. This is a ratio between the attach point and the tension.
Oh, okay.
This is not your mechanical advantage. This is just the force that's being applied to your attach point. It is not the ratio between W and T. So that W isn't even in here.
Okay.
So what you're looking for is an equation that has just W and T in it with some number.
Oh, okay. Sounds good. Thank you.
Great. No, that's a good question.
So I do have a question though, Robert. Like, so it is a 5/4. So 1 1/4 is of what the tension is, right? As far as the force on the beam, where does that extra force come from?
It comes from here.
So
So
are you pulling on the rope essentially?
yes.
Okay.
So you have, if you were to do this, this whole thing as a free body diagram, the whole system, you would have the weight, the tension that you're pulling down with to balance the attach point.
Okay, that makes sense. Thanks.
When we get into free body diagrams, and I love free body diagrams because it makes the whole thing easy. So I'm going to go back and share my screen again. And I'm going to show you a couple examples of what not to do. All right. Or an example of what not to do. So here's somebody's drawn a pulley system. They have one fixed pulley and 2 moving pulleys. And the free body diagrams for the 2 lower pulleys, P1 and P2, have been drawn. And even though it looks like there's 2 cords, and there's only 1 cord in this system, right? If we follow from mass 1, if we follow the line, it goes around and up and back to here. So we only have 1 cord. This is just sort of hanging in space. It doesn't really, it's not moving. It's just, it could be just an attach point for all we know. It doesn't make any difference. But if we do use the example of the fact that the tension is equal throughout the cord at any one point, and we draw the free body diagram of P1, look at P1 here. They've drawn the free body diagram, and you've got 2 T pulling down and 1 T pulling up. How can that be? That pulley is going to move, right? Because it's not balanced. It should be T versus T or 2T versus 2T, but because of the way that they've drawn this diagram, this pulley is unstable. It's going to move, and it's not going to move in a way that's stable. It's just going to accelerate away. So this is something that when you're evaluating your designs, to make sure that you don't end up with a situation like this. And this is kind of how you determine for sure whether or not that's happening or not. If this was a different cord, then it would work, but it's not. It's the same cord, so the tension's the same. This free body diagram is not static. It will not work. And what would happen is what we often call, when I go to see, is a 2-block system. One of these blocks would run up and jam itself against the other, and then it would be stuck, and nothing would happen, and would just either remain stuck or break. So don't want that happening.
What would it get stuck on?
Design. What's that?
What would it be getting stuck on exactly?
I'd have to build it. My guess is that this is going to
Me
want to go
too.
down. That these 2 pulleys are going to ram into each other, and then this is going to run up there and ram into that. Eventually, they're just all going to be a big knot at the top.
So you're basically saying that we can't suspend pulleys from each other because they need some sort of attachment to keep them in place.
No, that's not what I'm saying. I'm saying that it doesn't make sense in this case. When you're designing, you don't want the same 2 pieces of line pulling down as the same one that's pulling up. I'm not
Yeah,
quite
this is
sure.
where playing with them on a pegboard would really yield a lot of intuition.
Yes.
That's unfortunate.
Yes, absolutely. And that's
You
why
quickly figure that out. Yeah.
This is why I'm trying to show it as a free body diagram and why it's important to draw the free body diagrams.
Yeah.
Yes,
Yeah.
often in lab I'd walk along and people would have this knot of pulleys, and this is exactly what happened. This is they made a system like this.
In order to make the system work in statics where nothing's moving, whenever you free up the system so you could make your free body diagram, basically whatever's on top has to be what's on bottom to equal out so it's not moving. So yeah,
Has to be in static equilibrium.
exactly.
So you'll be able to check those in lab here. So, ironically, you'll never see this as a problem given to you in class. You won't see this on a quiz. You won't see this on an exam. But in real life, since you'll be the one designing the pulley system, you could do this by accident. And that's why I'm bringing it up. And that's why this lab is different from just a practical, just a theoretical standpoint. Is that here we're actually saying, hey, don't do this. This won't work. They would never give this as a problem because you couldn't solve it. It's unsolvable.
Well, with statics.
In a design situation, yep. All right. So here's the assignment. And I've kind of given you the answers for the first two already, more or less. I just want you to give me two examples of a pulley that you've seen, so you kind of know that you're somewhat familiar. And the next one is to explain why we made the assumption that the ropes had to be vertical. Kind of want you to flesh that out so you better understand why we made that assumption in this lab. I've already touched on that, I think, 2 or 3 times. Also remember the first lab that we did where we had a weight suspended in the middle, and initially it was vertical, and then we slowly moved it apart and ended up with non-vertical rope. And then what I want you to do is design 3 different pulley systems. The first one of any of your choice, but it has to include 1 pulley and 1 rope cord, preferably not one that you've already seen today. The next one I want you to do is design one that has 2 separate cords so that you have to do that intermediate step of solving for 1 pulley system and the other, and then making the ratio apply to each other. And then lastly, I want you to create one that has a mechanical advantage of 9-to-1 or greater. And again, any combination of pulleys that you like, doesn't matter to me what system it is, so long as you adhere to these 3 design constraints. What I ask for each design is that you draw the overall system diagram so I can see what your design is. And then I want you to go through and work through each free body diagram. So each pulley, or in the case of a triple pulley, each triple pulley, or each double pulley, or each quadruple pulley, however you choose, but each rigid set of pulleys drawn is a free body diagram. And then I want you to solve for the ratio of the mechanical advantage, basically the W versus the T that you're pulling on, and then the force at each attach point. So all the things that we've already done, I just want you to do that for each of your 3 designs. So, just as a point, if you're struggling with the questions, as you can see, they're only 1 point, they're worth half a point each. I wouldn't spend an inordinate amount of time answering those questions. I would focus on the other part and then get back to that if that's causing you grief, like if you can't answer that quickly.
Robert, is there a agreed upon way to draw those attached pulleys you had that had 3 or 4 pulleys attached on one object?
So as I've drawn, as you can see right here, this would be my preferred way. If you try to draw them as they look, when you draw like this, it's going to make your diagram really messy. So
that's why I'm asking. So you want to stack
I would draw
even
them
if there's
on
3 or
top of
4?
each other,
okay,
like this, just diagrammatically. And you can see that my rope isn't perfect, and it isn't perfectly vertical. Like I said, we're making the assumption that they are. Space them out so that you can see them individually.
I gotcha. I'm just thinking about the question says something about 9 times the mechanical advantage, so a multiple pulley seemed useful. Okay, thank you.
Yeah, absolutely. Multiple pulleys are definitely in your solutions, I would imagine. That are a lot of attach points. All right. So what I'm going to do is put you in breakout groups, and then Andrew and I will come and visit. Does anybody have any questions at this point? All right, here we go. Breakout room, who comes?
Hey Robert, I think I'm a co-host now. I think because I signed in. I'm actually signed in as Robert, as you.
Okay, that's cool.
But
Beat me
I
to
don't
it.
know. Yeah, I don't know how to get into breakout rooms, but I got your invite, so I'll go to that. Not really
Yeah,
sure.
you're a younger me. I like that.
Yeah, more handsome. No, I'm just kidding.
I'm sure that too. You all right, Mackenzie?
Yeah, I'm good. Sorry.
Cody.
Hey, Rob.
All right, we'll put you back in somewhere, huh?
Yeah, thank you so much. I was with Peter Del Pret and Bon Williams, and then out of nowhere, we're just going over the questions. Out of nowhere, it just kicked me out. It was so weird.
Yeah, it happens. What room were you in?
I was with Bon Williams and Peter Del Pret, I think, or Del Prete.
Hold on a second. Let me make sure I find. Oh, you were number 7. Okay. Hold on. Put you
Thank
back.
you so much. Oh, thank you so much.
Yeah. All right, Cody.
Hey Rob.
Laura,
Hi, I had a quick question. On the example number one, where you have that one fixed pulley attached to the wall, when you calculate the mechanical advantage, it's just T equals W because that's the weight, and you know that the tension is the same. But so the mechanical advantage is not the sum of the forces in the Y, right? It's just what the mechanical advantage is?
are you talking about design number one that you guys are creating?
Yes.
Yeah. So when you're calculating, go ahead.
Yeah, so I have just one pulley attached to a wall, and so there's a force there that's going up, and then the load on one side, which is the weight going down, and the tension. So if I do the sum of the forces, go ahead.
We'll finish up.
If I do the sum of the forces, I have F minus the weight of the load, which is W minus T, right?
So let me go over here. So is it like what? I see what you did. Okay. Let me draw one for you.
Yeah.
Let's see if I understand what you're doing. So you have one fixed pulley at the top, right?
Right.
And then coming down with T, and coming down to a weight.
Right.
And so if you did, yes, if you did the sum of the forces, so I see what your problem, why you're having difficulty here. If you do sum of the forces in the Y equals 0, you're going to have minus T minus W, and then we're going to have F at the top, right?
Yes.
Plus F. So we got three unknowns, and so that's why you're having difficulty. What you have to remember is that if you did a free body diagram with just a W, let's do that. You just had W here, it would be T, because T is the same all the way around.
Right.
So T and W are going to be equal.
Okay. Oh, I see. So it'd be the force is equal to 2T.
At F, yes. Or 2W. Because T and W are equal.
Yeah, okay. And then the mechanical advantage would be F equals to the work is half the force.
So W equals T, right?
Yeah.
That's what we're looking for.
Uh-huh.
So the mechanical advantage in this case would be 1. So W equals T. What you're looking for is that final equation of W equals some number times T.
Okay.
In this case, the number is 1.
Oh, okay. So the mechanical advantage is your ratio between work and the tension?
Yeah, the load. I say W, it's not work, it's weight. Yeah, so between the weight or the load and the tension, yeah, that ratio.
Okay.
Hey, Robert?
Yeah.
Robert?
Yeah.
Could you come to breakout room 5 with me? I'm they're working on an interesting one, and I don't want to give them the wrong information. So, but
I'll
yeah,
be
it's breakout room
number 5.
Yeah.
Cody, did you get dropped again?
Oh yeah, I got kicked out again. So weird. I don't know because
Room you're in?
I was in room number 7.
Okay.
Hey, it's me, Destin. Welcome back to Smarter Every Day. It's time for the Pulley episode. These are like my favorite things in the whole world. I bought this one. It looks like a book full of clothes or something like that. Pulleys are one of these things that everybody knows about. They know that somehow a pulley will give you mechanical advantage, but people don't really understand it. We all pretend like we do, but the person that really shows up is really clever and they arrange it in a perfect
Hello,
way.
Rob. I have a question.
Yeah.
Let me.
Myra?
Hello. Let me show you. See if I can. I drew something like. I don't know if you can see it. Where is it? There it is.
Okay.
So for P3, would it just have force up and tensions up, so nothing down? How would I calculate that?
So you're talking about that middle set of pulleys?
Yeah, the
double
bottom
pulley?
one. Yeah, and I drew it there at the bottom, but I'm a little confused.
Well, let's talk about that pulley first.
Okay.
So everything on the right-hand side of your system there is rigid, right?
Yeah.
So you don't really need to, basically all it's doing is rerouting the rope several different ways. So it really isn't adding any mechanical advantage to your system at all.
Okay.
And you could have just done that with one rather than all three.
Okay. So that one wouldn't work. It's okay.
Yeah, I mean, it would work. It just, in essence, the only thing that's happening is on the left-hand side. It would have a mechanical advantage of 2 to 1.
Okay. Okay. I'll redo another one. Thank you.
All right, Myra.
Hey, Robert. Robert, are you there? Hey, do you have the power to put me back in a breakout room? My Zoom keeps crashing, but this time it didn't just reload. I think I was in room 6. I can't hear you.
Sorry. Yeah, I don't know how to actually put the breakout rooms. I could put you in a waiting room. Hold on. I'll be right back.
Okay.
Shoot. Sorry, Mackenzie.
That's okay.
Yeah, I don't really know how this the Zoom thing works because it's not giving me access to put you in a breakout room for some reason.
Okay, that's fine. I'll just stay in here and work on it.
Yeah, I could help you though with whatever you're working on.
Okay, I think I'm good right now. I'm on
Okay.
number 2, so.
All right, yeah, just let me know if you need anything.
Okay, thank you.
Uh-huh.
Hey everyone, Farah from Zoom here. On this brief video, we're going to show you how you can leverage our breakout room feature to take a large meeting or virtual classroom and split it up into smaller groups or sessions. You'll see that I've already enabled the breakout room feature, which you can find in settings along the bottom, and that breakout room button will actually be right here. This is a button that only your host or co-host will be able to see. And right now we don't have a co-host in the session. If I manage my participants, I can hover over Catherine, for example, to make her a co-host. When we're ready to split the group into smaller sessions, I can easily click this button to the pop-up window, asking me how many rooms I'd like to assign out and how many participants per room. For this example, recommending since there's 6 people, we can split it up into 2 rooms. I can do this automatically or manually. Just click on the automatic button, it'll generate those breakout rooms for us. Certainly if there's anyone I want to swap out, maybe I want to move Michael to the other room, I can change him for a different participant. Once I'm ready to open all rooms, I'll click this open all rooms button, and our participants will be able to join the sessions that we've created for them. So we'll slowly see those people join. One thing that's really important to note is that as a host or a co-host, you can actually hop between the different rooms to talk to the participants. You can see here I have the join button. Now we're
What happened?
Is this on one? Yeah. He's not a one-hit shutout with Bumberger.
I had a question.
Uh-huh.
When you know how he showed us the pulleys that are stacked on top of each other?
Yeah.
So when you use those, because when he showed the example, he had 2 that stacked up on each other on the top and in the bottom
Mm-hmm.
to pull one weight. Would you just be able to use one? Would that work in real life? If you just had one and then you wanted to pull like something from a pulley next to it? Or does you have to kind of
Did Robert leave? I guess so.
Yeah, I don't know where he's at.
Or he's talking to other people. Okay.
Okay, yeah.
All right. Thanks. Take it
this-
easy.
Yeah. So Laura, what can you say that again? Sorry.
does the pulley have to be set up like how he did it like this?
Okay.
Or can you just have it that one? How would the strings go if you just have one and you have another pulley here?
Oh, to the right? You mean a pulley to the right?
Yeah.
Would the pulley to the right be attached to the wall, or would it be free floating?
It would be movable, but attached to the pulley on the side. Or would you have to attach it? I don't know. I just can't visualize it, I guess.
Yeah, I mean, if it was to the right, you could have the rope that you're pulling attached to it on one side, but then the other side would have to be attached to the wall.
Right.
And then when you pull the pulley, that pulley attached to the wall, it would still be able to move up and down as you gave it, as you pulled it, it would move up until it hits the top of the wall, right?
Right. Yeah.
And then if you let the slack go, it would drop down a little bit. So yeah, I mean that could work as a system for sure.
And then, but the ones like that are in the up and down, would that string get tangled at all if I put one here on the right?
Well, you'd have to design your system in real life so that way that wouldn't happen, which you totally can.
Okay.
It just makes it a little bit more complicated to get it all right. But that's the whole design thing of depending on like, okay, what are you pulling up? What is the room where the pulleys
Yeah.
are in? Like all that stuff. Yeah.
But we're in ideal conditions, so I could say that it's not going to tangle up.
Yeah, exactly. Yeah, it wouldn't. It wouldn't if you made it that way. Yeah.
Let me try it out.
Zoom's so annoying. I don't know what happened. I'm like a co-host, but now it's not allowing me to go into breakout rooms anymore.
No.
So annoying. Microsoft Teams, I don't know if any of you guys have used that, but I heard that's a really good like video online source. I don't know why everyone just defaulted to Zoom as like the number one.
Yeah.
Yeah, I like Teams.
Yeah. Hey Jason, got a what's his name? Mark Paxson of Oxford Instruments X-ray Technologies. He contacted me to see if I was interested in an internship.
Mark Patton.
Patton, yeah,
Yeah.
that's it, Paxson, yeah. Did you get one of those?
Yeah.
Did you apply?
Did I apply?
'Cause
Oh, did I respond to his email?
Yeah.
Yeah, I have an interview, although the problem is I think it's not going to work out. They want me to start, like they want me to do it over the top of the semester.
Oh, okay. For sure. Yeah, yeah, I have like an interview on like a video interview on Monday and Wednesday or something. So, but it was really vague on like when you would start to be working, like all that stuff, all the hours and whatever. But
Yeah, I think they're saving those details for the interview.
yeah. Yeah, I was curious to see how many people got contacted. Seems pretty cool though.
Yeah, it could be. Did some background research into X-ray tubes and how they work and rotating reflectors and
Yeah.
what they're used for imaging and mammography, and there was actually probably one of their competitors sprang up at the Brommer complex where I was working. One of our neighbors had a glass lathe and they were expanding quickly. I forget the name of the place. Also doing X-rays. They had a real good TIG welder. I mean, he could lay the finest bead. It was really cool.
Nice.
Half of why I wanted to get into TIG welding, because it's just because of what he could do. It was so clean, incredible.
Nice.
Yeah, would you do it if it was over spring semester?
I'd fucking do it right now. Yeah, my thing was they were asking for SolidWorks, and I am doing that next semester. But I have AutoCAD and other stuff. But I mean, I'm assuming a lot of it's just gonna be like writing, like drawing like manuals and like components in like a formal document, basically. You know, it's not like you might be present when they have like meetings and stuff, but you're not gonna actually like contribute to the design. It's more just taking whatever they design and then putting it on a formal internet site or something. I don't know, computer program. I'm not totally sure. Yeah, it's kind of guesswork right now.
Yeah.
But Miguel worked
I was
there.
gonna say, you know who would now.
Yeah, Miguel, I should hit him up. Fuck, I should hit him up for sure. But he got it. You know, he got a full ride to Berkeley. Full ride. It's crazy.
He's a bit of magic. That
Yeah,
boy.
yeah, dude. Good for him.
Pretty amazing. I mean, he's got an incredible story, and also,
Yeah.
he's just really, he aces classes, man. He eats that shit like for breakfast.
Yeah, and he's he's tutoring in the STEM center and
Yeah,
constantly involved. Did the
constantly involved.
engineering abroad, yeah, all that.
He's a bit of a superstar. Yeah.
Yeah. Yeah, I was also looking online and it said essential personnel only on the facility because of COVID. So I'm assuming a lot of the work would be remote too.
Well, I mean, yeah, I mean, even including the summer, I think. Oh, he did say he was going in, I think. But he may at this point be much at a higher level of essential than a intern.
What classes you taking?
4D and 45.
Nice, yeah. I should have done 4D. I don't know. I got a big load on my plate right now. I was like, oh, it's a fun class, but I don't need it. And yeah, I don't know. Should have done it though. Is it sick?
It's sick.
Yeah, I bet. It's all the new stuff. Like, oh, this is how it actually happened.
Yeah, we left off in the physics series. A, B, and C left off in 1885.
Yeah, that's so weird too. That's like the foundation of the course still, you know. Hey, Robert, you there?
Yeah.
Robert Sr.
I don't know what happened, but now I don't have access to breakout rooms. So, but it still says I'm a co-host. So I don't know if you assigned me to something. That might be it. But yeah, I don't know what happened.
Not that I know, but I can.
Yeah. Huh.
Oddly enough, it shows Mackenzie's not assigned to anything. She must have dropped out and come back in. I can.
Oh
fix
yeah,
it in
she
some
was trying to Mackenzie was trying to get back into her group, but it didn't give me access to do that. I think she said she was in group 6.
Yeah, my internet's been unstable all class, but it's been crashing, but then usually it just throws me back into my group, but this time it didn't. So I had to completely restart my
I'll put you
computer.
back in 6.
Okay, thank you.
Yeah, and I think there's a way that you could click on my profile and you can enable me as a co-host or to have privileges.
Let me send you to room 8 for to help people. How about that?
Okay.
Now.
Alrighty. Also, how long are they going to be working on this? Is this kind of like till the end?
They have till noon. Class is officially over.
Okay.
So at this point, I'm just here because people are struggling. It seems like.
Yeah. Okay. And yeah, I'm gonna be staying an hour after class, up to an hour after class, anyways. So, wait, is class technically over at 11 or 10? 10. Okay, sounds good.
I usually hang out for a while, depending on my schedule, what I got going. But.
Perfect. Okay, I'm gonna join the room.
And Jason?
Huh?
I'll have to figure out a way. I'm not quite sure. When I asked for the assignment to be handed in, I know I can pick students, I think individually, to make a later time. But I'm not so sure then how do I address everybody else, but I'll figure it out. You say you have a class right after this, or you have a class?
Yeah, I have another lab.
Okay. So was the 8 p.m. time frame sufficient for you to do all the things that you normally do on a Friday?
8 p.m.
Yeah.
Well, it certainly
I
wasn't
feel,
for the first lab.
well, the first lab everybody struggled, so that one we're redoing. So,
Um,
so
yeah, I
the
thought.
idea is you double time. The question is between 9:30 or 9 o'clock in the morning and 8 o'clock at night, you have 7 hours to devote to this.
Yeah, that should. I mean, that.
And that's the problem with the combinations is it requires a lot of extra time on your part.
Yeah. Well, I mean, that's just my life.
Yeah.
Yeah. Yeah, I think that sounds good, and if you can make that work, then
Yeah, today what might have to happen is you may have to email me the thing, but
that's
until I figure out how to sort people out at different assignment times.
Yeah, that's fine.
So
Angel has to do a meeting for engineering abroad at 10:30, and he said he's only on question 2. So because he has today's not gonna have enough time, and he was wondering if he get an extension on when he turns it in.
Go talk to Angel.
Okay. Yeah, he's in room
That's
8.
Right?
Yeah. And I have access to all the rooms. Oh wait, no, I don't. Shoot. Dang. Maybe you assign me to a different room.
Yeah, where would you like to go?
Wherever there's the most people, I guess.
Let's put you at 9 for now.
Okay.
Is there any way to do design challenge 3, which is without 18 wheels?
Yes. With less than that, for sure. It can be done with 10, for sure. So the simplest way, Jason, in this particular case, is you could use a multi-rope system. You'll notice that each multi-rope system is kind of like a multiplier for the most part. It's a very broad compass statement, but the easiest way to solve this is probably to do what they do in, like at the end of train hoists and stuff, is they use a multi-pulley block. And just put a bunch of pulleys at the bottom and a bunch of pulleys at the top. They're all in one big block, and leave it with one rope.
And that would take 19. I'm sorry, that would take 18 wheels.
No. So the simple way to look at this, let me, anytime you have a single strand rope system, for the most part, if you cut off the pulley where the weight is hanging from and you count the number of ropes, that is going to be your ratio. So that's including ones that are on both sides. So on any given pulley, on a one pulley system with a pulley at the bottom, the weight hanging off of it, there's 2 ropes going up. That gives you 2 to 1, right?
Sure.
So that's 2 to 1, just like in, you have 2 ropes going up, tension going up, weight coming down. 2T equals W.
Yeah.
2 to 1. How many pulleys did we have?
Well, 1, but in order to have another, yeah, sure, 1. But then do that again with only adding, do that same trick again where you now have a quarter of the tension, but only add another pulley.
I suggest that you draw one with 5 on top, 5 on bottom, root your ropes, do a free body diagram, and tell me what you come up with.
Deal.
Rob.
So, Miles, where are you sitting?
This is my work. Luckily, no one's in today. Which I'm not really sitting, I guess. I'm standing because I was standing there. Where
do you work?
Nice.
That's gorgeous.
This is in the Wrigley building.
Oh.
Oh.
In Davenport?
Not in Davenport. It's like
Wrigley building
right
is on the
off
west side, isn't it?
Gun factory.
It's on the west side, isn't it?
Mm-hmm.
Hmm.
Yeah.
So, Miles, my office is below you.
Oh, really?
You're on the second floor, right? Yeah.
No way.
I'm in the building, yeah. So,
no way.
I'm on the first floor there.
Stop by sometime.
So when you go out that funny little door, there's like one door to access all those upper rooms, right? The staircase. If you look, that's to the right as you enter the building, that would be the USTS entry. And you can also see the big boat outside the yard. That's our boat.
Oh, cool.
My office is right behind the big boat.
No kidding. Well, I have to visit and say what's up sometime. So, Bob, I wanted to run this by you. This is my pulley. This is on here.
Okay.
Would this?
Yeah. So
This
Jason,
would
there's
work,
5
right?
pulleys, and you got what, 10 to 1, right? So
yeah,
I'm glad you do this as a kind of do it. Now I've talked about this. This mathematically is absolutely correct. It gives you 10 to 1. It makes it hard to draw the free body diagram because each of those pulleys looks individual, but they aren't really. They're kind of like a block. What happens in that particular system is when you pull on the rope, I think on yours it's the left-hand side, you'll find that the bar will raise on the left-hand side first and last on the right-hand side. Again, mathematically, and for this class, that is a perfectly okay submission. But in reality, you would find that pulley would lift to the left first, because the rope as we talked about, to get a mechanical advantage of 10 to 1, you have to move the rope 10 times, right? Relative to the distance. But you'll see all the way on the right-hand side, the ropes can't move at all because it's
Totally.
so
Totally.
distance having to travel, and it decrements or decreases as you go to the right.
Yeah.
So what happens, it lifts in this sort of odd
Mm-hmm.
fashion.
Yeah. You wouldn't want
Works.
that.
And I gave a link in the chat box to a guy who did something almost exactly like that. I think he used 8 to 1, and you can see it happening. And he talks about why that's happening in that video. But it's for the class, okay. So I would I would draw the free body diagram of those 5 lower ones as one unit.
As one unit, yeah. But what if
The bar,
for example, what if I had like this lower beam as like a joint connection that joined my lower pulleys together, so that I then could hang off my weight like this, like that.
So that's exactly what he did in the video, and that makes those pulleys kind of like a block system. Yes, and that helps draw the free body diagram, because now you can draw that whole free body diagram with all 5 of those pulleys and all of the tensions going up as one thing.
Mm-hmm. Cool. Okay.
Like I said, it'll still lift weird, but diagrammatically and free body wise, that works better.
Mm-hmm. Cool.
I'm going to take a small break here. I got to visit the restroom. I'll be back, guys. So Miles, what you did is you're drawing this equivalent this way and then hanging the weight from the middle, rather than drawing it this way. That's about the only difference. It's certainly easier to draw the ropes going up and down this way.
Right, which is why I tried to do this, because drawing them vertical got kind of messy. So I was like, how can I do this better? But yeah, it wouldn't.
I don't mind the mess this way, so long as I can kind of follow it and you sort of know when you draw the free body diagram. Half the reason that these wheels are different sizes is so that they don't lay right on top of each other. That's why they're different diameters. So that when you put it together, they tend to keep separate from each other. If they were all the same size, then the ropes would start rubbing on each other, and it's also hard to draw.
Gotcha.
Let me go check on a few other groups here.
This is how I ended up drawing mine. I just made one very long pulley.
Nice. 3D.
Wait a
And
minute.
for the free body diagram, I just did that.
Wait a minute.
What? What?
I don't have a good feeling about that.
Robert was fine with it.
Is that a cylinder?
It's a cheap way to draw 5 pulleys.
Uh-huh.
Yeah, it's 5 pulleys in tandem. Although I think if we pretend that ropes can't stretch, a cylinder would work.
No.
Why not?
No, the pulleys are rotating at different rates. Miles, what do you think about that? Would that work to have a single cylinder? And essentially what you're doing is you're taking all of the pulleys that are in tandem and fixing them to the shaft. Does that accomplish the same thing?
I'm thinking. Yeah, I would have to draw it. I'm trying to. So basically, it's like a bunch of tandem means like stacked like this.
Yeah. And then suddenly you pin them to the shaft, so they all have to rotate together.
So the rope is like wrapped around the cylinder, or?
Yeah.
I'm trying to figure out. Oh, so it's almost like say you would have like grooves on the cylinder, sort of like a screw or something, or like a large screw.
Like a pasta roller.
With grooves?
Yeah, can you think of a pasta roller that has multiple grooves that are each it's a revolved form, so it can't be a screw. Screw is a helix. Right.
What do you mean by a revolved form?
Well, if you take a profile like that and then revolve it about an axis, like 5B.
So is this your section?
I mean,
right here.
Yeah.
That?
Yeah, that's your section, and you put an axis down the middle, exactly, and then revolve the form. So basically sweep that through space and create that volume, right?
What I was thinking was like,
I'm just describing how to create that the geometry in question.
Yeah, and I'm kind of confused on.
And so what you end up with there is essentially a pasta roller, right? That would create multiple strips.
This is what I saw from his drawing. Something like that.
Yeah, that's
Was
what
that
he had
was
on
doing?
his drawing.
Which I don't know if that would.
That doesn't do anything more than a single wheel. It's not. Yeah.
Yeah. It doesn't.
That's what we call in the oceanography business a capstan.
Yeah, it's a capstan.
Basically, it allows the friction of the rope to turn the big log, if you will. So often on the ship decks of ships, they have these logs that stick up that are powered, and you just wrap your line around it a bunch of times, and then by lightly pulling on friction will allow it to do all the energy work for you. And if you loosen a little bit, it slides off.
Yeah. So you get a multiplication of your own force by a fair margin.
I'm going to go check in on one more group, and I'll be back.
Oh, money.
See, what I would do is fix one more pulley on the right-hand side so that you don't have to stand on top of the beam to pull it up.
So what? All it does is change the direction. Nah. I don't want to add another pulley if I don't need to. Yeah. Right now, the challenge I'm having is a sort of a naming schema. Like these are the same. Should I call them the same thing?
Yeah.
Okay. These are the same thing. Should I call those the same thing? Okay. And then, so since those are the same thing, so now I have this force, and then my weight. So this is T1, and I guess for this one, this is T2. And T1, this is T1. So what mechanical advantage do I now have? Whoops. Because T1, 2T2 equals T1.
Well, your mechanical advantage is that you have that rope. You have two ropes attached to the beam, right? So it's like the beam is now doing twice the amount of, or it's holding up.
No, that's
No, yeah.
well,
no.
Well, I mean, that's not the question.
Well, that's your advantage, is that the beam is taking more of the force.
No, the beam could take an arbitrary amount of force and not help me.
Well, the beam, that's not the case. The beam is taking more force, which is helping you.
Maybe. That's not obvious to me.
Well, if you look, you have two connections to the beam, right? You have T1 and T2. So if you got rid of that right pulley, you would just have T1, right? So if you got rid of the right pulley, you just have T1. So that your mechanical advantage, then
So T1 is half of weight and T2 is half of T1. So I've done a 4 times mechanical advantage.
Yeah.
But I want to point out that it's not as you can, I don't think you can sort of count, like determine your mechanical advantage over the weight just by counting attachment points.
You can't just multiply by 2 and keep doing that.
Well, so for example, even in this example, how did I get 4 times mechanical advantage? How do you get from 2 to 4?
Well, you have 2 with just the one pulley, and then you're taking, you have twice the advantage of that when you add another one. So I would say if you have 3,
if I did this again, if I did one more.
If you did one more, would that be 6 or 8?
Yeah, I see. I don't know. Here's your reverser. So that's another attachment point. Does that fuck with you?
No, because you're just rerouting the direction.
Right, but if your technique was to count attachment points and say that those are...
Well, count attachment points that moving pulley attachment points, I guess. I don't know. So there, if you have 4, well, let's say if you have 3, just for the sake of simplicity. Yeah, so would be 8 then, because if I'm doing 1/4 of, so I'm putting in 1/4 the amount of effort with 2, and then it becomes twice as easy if I add one more.
It becomes
the
half
8.
that.
Yeah.
So think of design 3 as a challenge in terms of how few pulleys you can use. How few wheels can you use and get over 9?
Well, now you're making it a more complicated problem than I asked for, but it's a good question. In reality, that's what I want to do is the least
Right.
amount you can do,
So
most
we're
you can do for the least amount you can possibly spend.
right, exactly. So we've found that this system is maybe what you were referring to as the force multiplier is a 2x. Every time you add a pulley, it's a 2x.
Yep.
So I can get over with just 4 pulleys. I can get basically 16 times mechanical
2 to the
advantage.
4th.
What's that, Robert?
That's 2 to the 4th. So yeah, you're multiplying by 2 times each time, 4 times, you get to 16 real quick.
But you have to do 4 separate equations, so.
Yeah, and 4 different chords, so you kind of
the
math a little messier, but it absolutely is a good way to go. So.
Well, whatever. I'm on design challenge 2 anyways. So, Rob, I was trying to figure out how I would set this up in terms of like describing things. So I see that the weight is equal to 2T1. Yeah, 2T1 equals W, and 2T2 equals T1.
Yep. So what you're really after is the ratio of W to T2, right?
Right, I'm trying to get that.
Substitute in.
Right, so then I just multiply this top equation, so then I get, oh yeah, let's see. So there's a bunch of ways I can do this. So then I get 4T2 equals W, or T2 equals W over 4.
And your 2 attach points, T2 of course equals T2. So your attach point on the right-hand side is T2. And you know what that is relative to W, which is 4 times, or 1/4 of W.
Okay, so mechanical advantage. Yeah, attachment point. Wait, what's the question? It's the ratio of the force to the attachment point. So attachment point T1.
It's going to be half of W, right?
It's got to be half W, yeah. And T2 is a quarter of W.
Yep.
Okay.
That's it.
That's it. But now, let's see. There are a bunch of ways I could do this.
Hey, Miles, what company you work for up there?
Right now I'm working for Andrew Radovan Civil Engineering, which is basically just basically I'm just doing craft work for we do mostly structural engineering and civil too, but like mostly structural stuff. So it's been pretty cool.
Okay.
Yeah.
You know, we had any engineering firms upstairs there. Cool.
Yeah, we're in the corner here. We're pretty hard to find, but I like the
That
big
whole area up there is like a big mystery.
Yeah. Well, it's funny because the downstairs is a mystery for me because I've never really been down there. So I guess it's just a different perspective.
Yeah.
So yeah.
All right, guys. Well, I'm going to check out.
Same here. Thank you, Rob, for the help and all.
No,
See
there's
you
not
guys
many of you
next
left,
week.
so. Jason, I'm going to be ending things real soon here, so I'm going to go check in on the last breakout room and then check out.
Yep.
Thanks, Rob. I'm just gonna send mine in. I think I got it.
What the hell? This is not good.